folks, so today we're going to be working a little bit on the macroscopic and different charge states of amino acids. And we're going to start with glutamic acid, which has a titratable R group. It has a carboxyl group here on the side chain. It also has a backbone amine and a backbone carboxyl group. The pKa's for these groups are listed. 2.1 is typically the backbone. Anything around 2 is typically our backbone carboxyl group. Anything around 9 is usually our backbone amino group. And then side chain is our 4.07. So those are our 3 different groups. Now, if you remember, there's a quick way for us to tell how many possible there are. Of course, we could always say, protonated, deprotonated for each of these. But there's a quick way. It's 2, which is the number of states. So this can either be protonated or deprotonated for each group, to the n, which is the number of groups. So glutamic acid has 3 groups, so this would be 2 to the 3rd, 8 possible charged forms. And so this is asking for all of the macroscopic charged forms. And so we need to figure out which ones those are. So to start this out, I usually like to draw out a little generic ball and stick model. Now, I'm going to draw that out nice this time. Okay, I always put the N on the left here on the backbone and the C on the right. Those are always going to be there for any amino acid. So alanine, glycine, the isoleucine, anything is going to have those 2 backbones because everything at least shares the common amino acid backbone. But glutamic acid also has a protonatable R group. And so if there's an R group that's valid, I will that can be titrated, then I will draw it off the side of the R group. Now, if you have a nitrogen in your group that's titratable, then that starts out usually as a high pKa, and it either goes from positive or neutral. So when it's most protonated, it starts out with a positive charge with gained hydrogen, and after you pass pKa, it's going to switch to a 0 charge. And remember that switch is going to happen at a pKa of 9.47. Now our carboxy group and the backbone and on the R group are both obviously carboxylic acids, and those start out neutral when they're protonated, and they will lose their hydrogen to gain a negative charge. So for both of these guys, we want to have a negative charge when it's deprotonated. So I'll draw these as neutral, negative. And that's going to be the same for any OH or SH that we'll see in amino acids. So both of those can switch between neutral and negative. And those happen at pKa's of 2.1 again, or 4.07 for the side chain. So our macroscopic charge forms can actually be figured out using these ratios. Protonated states on the top, the deprotonated on the bottom. And so if we are looking at just those little cheats, no, they're not cheats, but they're handy little guides. If you look at just the top states, +1, 0, and 0, if you add those all up, you start at a +1 in the most protonated state. If we look at the bottom, it's the most deprotonated state, 0, -1, -2. And so these ones will go between 1 and -2 in integer values, because each of these can only switch in an integer from 0 to -1 or 1 to 0. So they have to step 1 at a time, and they have to go through 0. And so if I'm trying to connect my +1 to my -2, I have to go through 0. I'm going to subtract 1 each time. And that gives me my 4 macroscopic charge forms that are available out of 8 possible. Now, these charge states will flip as you pass through pKa's. And so I like to think about walls here that we cross. And underneath those commas that I drew, or under the walls, I'll put the sequential pKa's of the compound. And 9.47. And as we change our pH, we're going to switch from one state to the other. And this is going to be really helpful when we're drawing out our different charged forms. So for example, I'm going to draw out our 4 charged forms just as blank templates. So just 4 of these guys that are in equilibrium with each other. Oops. Off the screen. Draw these in equilibrium with each other. I'll scroll down a little bit for us. 4 of these guys. So that's just 4 forms. I'm going to draw them all in equilibrium with each other. This is a linear change, but I had to draw it to fill up space here. So we have 4 possible. One of them is going to be our +1. Then we have a 0 form, a -1 form, and a -2 form. And to appropriately put our pKa's onto these guys, we need to check our little guides. So for example, the N in the most protonated state is going to be +1, C is 0, R is 0. And altogether that'll give us a +1. So our +1 form is going to look like this. Okay. Now, as we pass our pKa of 2.10, we are going to switch our C-terminus into its other charged state. It's going to deprotonate at the C-terminus. And so that means that this C-terminus is now going to become negative, while everything else stayed the same. So altogether, you can see that this is actually a 0 charged form. That's our isoelectric form. Plus at the end, negative at the C, neutral at the side chain. Then we're going to cross through a pKa of 4.07. And at that pKa of 4.07, we are going to switch the R group. If you recall, our R group switches at 4.07 from one state to the other. And that is going to change our side chain from neutral and negative. So now we have one at the C-terminus, we have one at the R, and our N-terminus is still positive. So altogether, we end up with -1 here. And finally, we're going to pass the pKa at the N-terminus of 9.47, which is going to cause our N to switch from protonated and deprotonate to 0 charge. Our -2 form is going to be negative, neutral, negative, negative. So those are our 4 charged forms of our glutamic acid. Okay. So let's do a different one of these. Let's just try it with a different amino acid. Okay. So I am going to, let's try this with tyrosine. So tyrosine, we recall, is drawn its most protonated state. Tyrosine has a phenol on the end of it. On its side chain, a CH2 phenol. And our pKa's on this guy are 10.46 at the side chain. It is 9.21 at the N-terminus. And it is 2.2 at the C-terminus. Okay, so again, I'm going to figure out my charged forms by drawing out my blanks. At the N-terminus, we have positive neutral at 9.21. At the C-terminus, we have neutral negative at 2.2. And at our side chain R, we have neutral negative because it has an OH at a pKa of 10.46. This is going to look very similar to what we just did with glutamic acid. I'm going to quickly go through that and how we can quickly do this if you're used to seeing these things. So again, we're going to have a +1, a 0, a -1, and a -2. We remember the tops are +1s, the bottoms tell us are deprotonated. Goes from 1 to -2. and integer values through 0. And I like to put my pKa's down on the bottom to kind of keep me organized, and it tells me where I switch from one form to the other. Okay, so this is going to look exactly the same as the last. I'll draw this kind of on its edge. It doesn't matter how you draw these, just as long as they're correct. So again, we're going to look for our first charge form. It's going to be plus at the end and 0 at the others. As we pass 2.2, we're going to flip our 2.2 into its deprotonated state. So our C is going to become negative. Our N stays positive. Our side chain stays 0. We're going to pass 9.21. That's going to be for our plus 1, our 0. Our negative 1 form is going to be past the 9.21. We're going to flip that N into its 0 charge state. And so now we're going to be neutral, neutral, negative. And finally, at 10.46, we are going to flip that side chain to negative, and we'll have neutral, negative, negative. It looks a little different than the last one. We had slightly different forms of these guys as we went through, but this is the same process. So you'll be able to use this. I'm going to switch to a positively charged one. You'll see the difference there. So here we have arginine. Arginine is a positively charged at room temperature, or room temperature at physiological pH, and room temperature, amino acid. And again, we have a couple of key features of our amino acid. We have a backbone amino that you usually see, a backbone carboxyl group, and then we have a side chain guanidinium that is part of our side chain, and it's going to become protonated at physiological pH. The pKa on this one is 12.48. On the N terminus is our 8.99. Remember, those are always around 9. And then our side chain, our backbone carboxyl group is 1.82. All right, so a couple key things. We're going to show the macroscopic charge forms of arginine, and we're going to give the isoelectric point. Now recall that the isoelectric point is the pH at which we are most likely to find something with 0 net charge. It's not as easy as simply averaging all 3 pKa's and figuring out what they are. You need to figure out the ones that are on either side of the 0 charged form. So it's important that we do the macroscopic charge forms, draw them correctly, and then use them to find our isoelectric point. Okay? So I'm going to do my charge forms. We can do this really easily again, just like we did on the last two. Our N is positive, neutral. At the pKa of 8.99 it switches. Our C is neutral, negative. At the pKa of 1.82, that will switch from one to the other. And our R group has nitrogens in it, as you can see. If it contains titratable nitrogens, it is also positive, neutral. And this is a pKa of 12.48. So our charge forms are going to go plus 1, plus 2, plus 0. So the top charge forms are plus 2. And the lower charge forms are negative 1. And remember, they have to connect through 0. So if I'm going to get to negative 1 from plus 2, I have to subtract 1 each time. I'm going to put my pKa's down. Okay. And now let's do our 4 charged forms. That's not pretty. There's 1. Oh, that's big. 2, 3. And that's at equilibrium with the 4th. And remember, these are going to represent our plus 2, our plus 1, our 0, and our negative 1 forms. So I like to start with the plus 2. Plus 2 is easiest because we can just read across our little shorthands. Plus at the end, plus at the R, 0 at the C. To get us a plus 2. So we're going to do plus, plus, 0. Now what's going to happen is that the first pKa, as we cross that pKa barrier, it's going to switch from the +2 to the +1 by changing at that group. So our 0 is going to flip to negative. Our C now becomes a negative charge. Our N and our R group did not change. That's our +1 form, +1 + 1 - 1. And that's going to happen at a pKa of 1.82. And then in a pKa of 8.99, our next group is going to switch. Our next group here is that N-terminal nitrogen. That's going to go to 0. And so in our 0 charge state, we're going to have a 0 at the N, a positive still at the R group, and a negative here at the C terminus. And finally, at 12.48, that side chain quantity is going to lose its charge. It's going to become neutral at the deprotonates. And so we're going to end up with neutral at the N, neutral at the R group, and negative at the C terminus. So those are our 4 macroscopic charge states. This question is also asking for us to give the isoelectric. And so that is going to be the 2 that are on either side of our 0 form. The average of those 2. In the middle of this region between 8.99 pH and 12.48 pH, we are going to get the maximum concentration of our 0 charged amino acid. And so to find the isoelectric point, we're going to plug it into our equation. Pi is the average 8.99 plus 12.48 divided by 2. And I get a Pi equal to 10.735. 10.735. That's the average of 8.99 and 12.48. So at a pH of 10.735, we are most likely to find a 0 charged arginine. So I hope that helps, folks. Thanks.